This is the elementary scheme of the experimental setup in electrophysiology that you have already familiar with in your theory. And so to understand how this device functions, because quite often there are elements, especially in the area where you are configuring your experiments, which act as basic electrical elements, and you have to understand how that functions if you have to interpret the data correctly, especially when the configurations are often quite flexible. So let's look at where the basic circuit elements may arise in this configuration. Here is a conductor. Here is a conductor inside the container in which the symbolic neuron is there. So this conductor and this conductor can form a capacitor, right? Here it's connected to this silver chloride wire, and this is connected to this silver chloride wire through the saline. So this is saline, right? And this is depending on a conducting solution. Whatever electrolyte you are going to use. The other electrical element would be here. This passage is extremely narrow, and so it's connected to the inside of the cell through these chain of resistances. And of course, at every point there will be capacitance connected to the external or the bath or saline. Of course, you are already familiar with the circuit element here. There is a capacitance across the membrane, and of course if there is a channel here, then or a collection of channels, they are also connected to form. Okay, so in effect this is connected like this, right? So there are combinations of resistances, capacitance, series, parallel, and so on in this configuration, and depending on where the position of the electrode is and so on, these resistances can vary, right? The surface area change where you are recording from, all that affects this capacitance and this channel conductance. Okay, so let us start with very basic circuit element that we, or motif that we may encounter. A couple of resistances in series, and that forms what is called a voltage divider. And so that's the first circuit motif that we will look at. And in order to look at any of these motifs to see how they function, we need to have an actual circuit built with some voltage source. So as I said, we will be using this Arduino for most of our studies in terms of as a small computer. Not only that, we will also use it as a 5-volt voltage source, because if you plug it into the computer using this USB port, now it is powered, and as you can see in the schematic, there are a number of channels here, and there is also a provision for taking out the voltage and the ground from here. Okay, so if you look closely, I don't know whether you can see, here is a 5-volt input and here is a ground. So I will basically take two wires, two jumpers, and black I will sort of, for easy recognition, I will use this as the ground. So here are two grounds. I will take one point of ground and then say make this point my ground. Okay, that means now this entire row is ground, and I will take one point here and put it here, and that makes this entire thing. Okay, now of course we have to check whether these have actually formed the voltages. So we can see the voltage by using our multimeter. We turn on the multimeter, we change the measurement to voltage, and we are expecting 5 volt. This is not an auto ranging multimeter, so we have put in 20 volt range. We can, before plugging in, we can actually take this out and check if the voltage is, yeah, it has got 4.96 volt. So we'll note this down. Okay, so you should have a lab notebook, so you should note that in the lab notebook. The voltage that we have equal to 4.96 volt. The basic circuit element or motif that we are going to study is what is called a voltage divider, meaning if there are two resistances connected like this, okay, what will be the voltage across? And you are all familiar with this, R1, R2, and we are going to measure across this what is V out. Okay, so we know this is 4.96. So now let us take two resistances, just randomly chosen resistances, and I have chosen one to be around 10K and the other to be around 49K. Okay, so we'll check whether that is true. For that we need to switch this into ohm meter, right? So 49 in the tens of K's range, so I will take in 200K range, and then I am going to measure this. So here is the measurement of one of these resistances, and it is showing 441, and you can see if I hold tighter it is changing. So I would leave one of my hands from the probe and then touch here. Okay, so then now it's reading 45.7 kilo ohm. If I touch the probe, you'll see that the resistance is going down. That's because now my body is coming in parallel with the resistance. Okay, so when we make measurements, especially larger values of resistances, we should make sure we don't touch at least one side of the probe. So we have got a resistance of 45.6 kilo ohm. So let me write it down. So R1 equal to 45.6 kilo ohm. Okay, now this one is supposed to be 10K and I am getting 9.7 kilo. So this is 9.7 kilo ohm. So it's a 5% tolerance resistance, because you can see a gold ring on this side. Okay, yeah, so we have two resistances. Now we have to wire it up as if it is a voltage divider. So the way to go about it is we have to identify where is this power point. Okay, so first we are going to wire up this to be 45.6 kilo ohm. So we have identified this point. This is a plus voltage that is here, and then I am going to so I have to connect one resistance point at that. Yes, now that means this resistance is now connected to this terminal of the resistance is connected to this. Now we have to put this point somewhere, right, where we will connect this resistor. So let us put it somewhere here. Okay, which means now this lead is now in contact with all these points. So I can put the other resistance for this point anywhere here, right? Anywhere here. So that is now we need this point to be connected to the negative terminal of the power supply, so which is here. So I am going to connect it here. Okay. So these things are connected. Yeah, so this is the point where this connection, this is the point where these two connections, this is the point where this is connected to this. What should be this measured voltage that we should predict, right? So we have 4.96. So we can use swing 9.7 into 10 raised to 3. All these 10 raised to 3's can be cancelled. So what's that value? So let us use Octave to do the calculation. 4.96, 45.6. Okay, and so we are expecting a voltage 0.87 voltage. So now let us use multimeter to check to voltage range. Let me put in 2 volt across R2 9.7K, right? So positive lead I'm placing here, and So our prediction was 0.87. Our prediction was 0.87, showing that how nicely the theory works in this case. Next, we look at another circuit motif, RC circuit. And this occurs in a number of situations. For example, in this petri dish, there is a neuron like that, so symbolic. So this is the path, and here is electrode coming in, going into the cell, and so this becomes a narrow conductor, so high impedance. And then at the cell, of course, there is a capacitor, the bath. So through the intracellular medium, it is connected to this plate of the capacitor. So this forms a connection from the amplifier coming in. Let us say this is an amplifier connected here, okay, plus that to the ground. And this is in such a way that this amplifier can apply either currents or voltages into the circuit. So now, if suppose we were to apply a step voltage into this at this point with respect to the ground, then of course this through this resistance, which we call R1, and we'll charge this capacitor C1 to whatever be this voltage we applied, let us say. So let us say it's initially held at 0 voltage, and then we step it up to this VA. What would be the behavior at this point? So let us call this point A and this point B. So what will be the behavior of the voltage at the point B, that is across the capacitor? That's what we want to figure out. And we already have seen theoretically that it should start from 0, because initially there is no, the voltage across is 0 because applied voltage was 0, and then it will charge towards the VA, right? And it will reach VA asymptotically. So this is VA, and it will charge to 95% of the voltage in 3 tau, correct? This time should be 3 tau, and tau is RC, in this case R1 C1, right? So question is whether we'll be able to see this effect clearly. And to get the start off, we will use a very large capacitor charged through a fairly large resistance, okay, R1 C1, and to see the effect. So let us first measure the resistance across the R1. Okay. The resistance R1, I am connecting from the VCC to the point where I will connect the capacitor. And this lead here is basically connected from this point just for convenience, so that I can insert it into the breadboard. Okay, so that is a positive lead of the multimeter. Now I want to measure the resistance, so I am going to put it in the ohm meter, and this is an auto-ranging multimeter, so I don't have to choose the range. Okay, so this is a different one from that we have. So this point is our positive, and so I have to measure the resistance here. So it is showing to be 9.75, and actually it is supposed to be 10 kilo ohm, so it's a little lower than that. It is the 5% tolerance. Now this capacitor is 2200 microfarad. So in our case, R1 equal to
9.75 kilo ohm, and C1 equal to 2200 microfarad. Okay, so tau is equal to R1, C1 equal to, if you calculate, R1 equal to 9.75 into 10 raised to 3, C1 equal to 2200 into 10 at minus 6 farad. So R1 C1 equal to 21.6 seconds. So 3 times that, 3 tau is 64 or 65 seconds. Switch this to the voltage range, and so we are going to check whether this capacitor has any charge by checking whether there is a voltage across it. Okay. Otherwise you have to discharge it. Charge voltage, I think, from previous charging. So I will take a resistor, so this one, and connect to the two sides of the capacitor to discharge it. Okay, now there is nothing that we are not connected to the multimeter, but we just discharging the capacitor. And just to make sure that it is completely discharged, I will just touch the leads. Okay, so it should be now completely discharged. So if I check the voltage now across the capacitor, it should show very small voltage. I can see it is around 30 or 40 millivolts. Okay, 30 or 40 millivolts. So that means we are fine with the capacitor. So now to make our measurements clear, I will insert the positive lead onto the positive points, power coming from the Arduino, and I am supposed to connect this to the ground here, right? But I should be ready to read the voltage when that starts. After that, I will maybe put a stopwatch here. Hopefully you can see both. So I am going to take this one and connect to this point. Right now, naturally we are measuring the voltage across this point and the ground without the capacitor, right? So it's reading 4.72. So our V is 4.72. So this is 4.72, right? Okay, volts. Now, ideally, because the voltage across the capacitor is 0, the moment I plug in, it should go to 0. And then I will start the stopwatch at the same time. Okay, so I will plug in and start the stopwatch. And 95% of 4.72, that is 0.95 into 4.72 is 4.48. So we will stop when the voltage reaches 4.48. So that's when I will stop the stopwatch. So I will plug this in, start the stopwatch, and then stop at 4.48. Plugged in, started the stopwatch. So it had gone to 0, it is rising. So we'll wait for 4.48. Then I will stop the stopwatch. Yeah, it's going towards 4.48 asymptotically, as you would have expected. Now its changes are slower. Yeah, so it took 1.08 seconds. that is 68 seconds. So we had predicted that it should take 65 seconds, but we took 68. Not very bad. There could be some internal resistance of this power source through which it is charging. So the tau that you will be calculating will be always a little less than the actual tau. It's not an ideal voltage source. Now this is the capacitor that we have charged. So according to theory, this capacitor should be now storing that charge. Now say I have not connected any elements to the leads, it is simply connected to these breadboard points. So if I measure the voltage across the capacitor, we should see around 4.7, which was the output voltage from the Arduino, right? So it's at least without any load, it has maintained the charge near 4.7. Now, can we use that charge to drive some device? So we will use this LED to test it. So this LED is light emitting diode. I have put its cathode here and anode here. Now I'll use this 470 ohm to power it. So let us see whether it works. I'll plug in point here, then I'll connect it to the Arduino power source. Yeah, it is lighting up, as you can see. Can I use the capacitor to power it? That's the question, right? So now for that I have to connect the cathode to the negative of the capacitor and connect to the charge point, and I have inserted the other lead in this position. Okay, so it's not connected anywhere else. Now we have to power this LED using this 470 ohm. I will now connect it to the positive, and you should watch closely now this LED. As soon as I connect it, it should light up and then gradually dim as the energy in the capacitor is dissipated. As you can see now, its brightness is decreasing and it is now gone off completely. Okay, very clean, it is lit. So you can see that charge stored on the capacitor can actually be utilized as energy. Now the voltage across the capacitor, if you measure, it should be nearly 0. Why is it not 0? Yeah, because I have not used the normal incandescent light but an LED. LED has a cutting voltage of 1.5 or so. So after the capacitance voltage has decreased below that, there is no voltage to drive the current through the LED. So that would mean that the capacitor will discharge up to the cutting voltage of the LED.